Okay, let's dive right into one of the wildest ideas in all of physics. Have you ever had that feeling that the world around you, this solid three-dimensional reality, isn't quite what it seems? What if it's all just a projection? Well, that's exactly what we're going to explore the holographic principle. And trust me, it's going to get weird.
And no, that's not from a science fiction movie. That's a direct quote from Leonard Susskind, one of the giants of string theory. He's saying that our 3D reality could literally be an image of information that's stored on some flat 2D surface. It's a serious proposal, and it completely flips our intuition on its head. It challenges, well, everything.
So, the big question is, how? How on earth could that possibly be true? Where does an idea this strange even come from? Well, it wasn't just some wild guess. This whole concept was born from a deep cosmic mystery. A paradox so serious it threatened to tear physics apart. And to get to the bottom of it, we have to start with the most extreme objects in the entire universe.
Right, our detective story begins with black holes. You know them, these absolute monsters of gravity where nothing, not even light, can get out. For decades, physicists were completely stumped by a really simple question about them, and the search for an answer, well, it kicked off a revolution.
Here's the heart of the problem. Imagine you have a book. That book is packed with information. The story, the words, the characters. Now, if you burn that book, the information seems gone. But technically, if you could track every single atom of smoke and ash, you could piece it all back together. But what happens if you toss that book into a black hole? Does all that unique information just vanish from the universe for good?
And this is where physics has a major meltdown. See, you've got two of our best theories in a head-on collision. On one side, quantum mechanics has this one sacred, unbreakable rule. Information can never be destroyed. Ever. But on the other side, you have black holes, which are shockingly simple. There's a rule called the no-hair theorem, which says once something falls in, the black hole only has mass, charge, and spin. That's it. All the unique info about that book seems to just get erased.
You might think, okay, maybe the information is just trapped inside. A reasonable guess. But then Stephen Hawking came along and discovered that black holes aren't totally black. They leak. They glow with what we now call Hawking radiation, and over insane amounts of time, they actually evaporate and disappear completely. So if the black hole itself is gone, where did the information go? Now it seems like it's really gone forever, and that breaks quantum mechanics. That's the black hole information paradox.
All right, so to solve this massive puzzle, physicists had to think about information and space in a totally new way. And the first huge clue, the first big break in the case, came when they tried to figure out just how much information a black hole can actually hold.
So you have physicists like Jacob Bekenstein who decide to tackle this problem head-on. Now in physics, the word for information content is entropy. Just think of it like this. The more ways you can secretly rearrange the atoms inside something without changing how it looks on the outside, the more entropy and the more information it has. So they asked, what's the absolute maximum amount of information you can cram into a black hole?
Now logically, you'd think that information fills up space, right? If you've got more space, you can fit more stuff in it, which means more information. So the natural assumption, the one everybody on the planet made, was that the information capacity of a black hole must depend on its volume. It just makes sense. Information should scale with a three-dimensional space inside. Double the volume, you get to store more information. But, as you might have guessed, that is not at all what they found.
What Bekenstein and Hawking actually discovered was so weird, so counterintuitive, it defied all expectations. The maximum amount of information that can possibly fit into a region of space isn't determined by the 3D space inside it, but by its surface area.
Yeah, you heard that right. The two-dimensional boundary, the event horizon. Just let that sink in for a second. The information isn't stored in the 3D bulk of the black hole. It's somehow written on its 2D surface. This discovery absolutely blew everyone's minds. So here's the takeaway, the really stunning clue. Black holes, which are the densest things the universe allows, show us there's a hard limit on information. And that limit is defined by area, not volume. It's almost as if that 3D space inside is just an illusion, and the real information is all living on the boundary. This clue was just too big to ignore.
And this totally shocking result from black holes gave birth to a much, much bigger idea. An idea that might not just apply to black holes, but to our entire universe. and it's called the holographic principle.
So here's the formal definition. The holographic principle says that everything needed to describe a volume of space, I'm talking about you, me, the Earth, the entire Milky Way galaxy, can all be fully described by information encoded on a surface that surrounds it. This isn't just some weird rule for black holes, it might be a fundamental property of reality itself. Now, credit where it's due, this revolutionary idea was first really put forward by Gerard de Hooft, and then Leonard Susskind took it and ran with it, giving it a solid home within string theory. They took that bizarre clue from black holes and said, hey, what if this is true everywhere? What if this is a deep truth about how space-time and gravity actually work?
So what does this actually mean for us? Well, the name says it all. Think about one of those holograms on your credit card. It's a totally flat, 2D surface, but when light shines on it just right, a full 3D image pops out. The holographic principle suggests our universe is like that, but on a cosmic scale. The 3D world we're all walking around in could be a holographic projection of information living on some distant 2D boundary at the very edge of the universe.
Okay, I know, this sounds like it's ripped straight from a movie script, but it has become a central part of theoretical physics. So why do so many brilliant physicists take this idea seriously? Well, it turns out it's way more than just a cool analogy. There's some incredibly powerful math that backs it all up.
The reason the holographic principle wasn't just dismissed as a crazy thought is because it eventually found a concrete mathematical foundation. It's not just a philosophical idea, it's a calculable relationship that connects two completely different-looking physical worlds.
The best evidence we have for this is something called the ADS/CFT correspondence. You can think of it like a Rosetta Stone for physics. It's a perfect mathematical dictionary that lets you translate between two very different kinds of universes. One is a complex universe with gravity, a lot like ours. That's called the bulk. The other is a much simpler quantum world without gravity that lives on the boundary. And here's the mind-blowing part. The math says they are exactly the same thing. Anything that happens in one has a perfect mirror image in the other. This even suggests that the fabric of space-time itself might actually emerge from quantum connections, entanglement, on that distant boundary.
And that brings us to the last, really profound question. This principle suggests there are two equally real ways to describe our universe. One is a 3D world with people and planets and gravity. The other is a 2D world of pure quantum information. So, which one is the real one? Are you really here in the 3D bulk? Or are you part of the pattern on the 2D boundary? The physics says both descriptions are valid. They're the same thing. And thinking about that, well, that just might change how you see everything.